Hi everyone, myself and Arun Kumar from SNS College of Technology in the Department of ECE. In this video, we are going to see about impulse and step response analysis of second order systems. The following things we are going to discuss about control systems. So, first one is introductions, second order systems, step response of second order systems, impulse response of second order systems, damping ratio of second order system, and total summary, followed by an assessment at the end of the slide. Second order system. Normally, the second order system is used for a large number of transfer characteristics equations. It is based on the number of systems which is used in the control systems. It is based on first order systems parameters t comma k, simply the changes the speed of the offset responses, whereas the changes in the parameters of the second order system can change the form of the responses as well as. The second order system can display the characteristics much like a first order system, or it can be depending on component values and display the damped values of the corresponding transient response analysis as well as in this second order system. So by using this, we can able to predict the del factors with respect to the different damped conditions. Let us consider the following block diagram of closed loop control systems. Here, an open loop transfer function is given as omega n square divided by s into s plus 2 into omega n is connected with respect to the negative feedback loop. So initially the transfer function of the system can be calculated with respect to the input of the systems. It is followed by omega n square and s square plus 2 del omega n s plus omega n square. So here the s square, the two value is nothing but second order system. So all the values are followed by the root of the corresponding transfer systems. So initially the corresponding transfer functions has been depend on two factors. One is omega n, one is del. Omega n is undamped natural frequency. It is the second order system which is frequency of oscillation of the system without damping. And next one is damping ratio. The damping ratio of the second order system, which is a measure of degree of resistance to change in the system output. So while considering the second order system, so these two parameters are very useful to identify the corresponding frequency of the control systems. And next one is problem. Determine the undamped natural frequency and damping ratio of the following second order systems. So here they are given about on problem. We are going to discuss about the damping ratio as well as the damping natural frequencies. So it can be calculated as omega n square equal to 4. So initially omega n equal to 2 because it is a second order system. It is 2 del omega ns. For the omega n is nothing but 2. So based on the value, we can take it as a natural frequency omega n. So followed by del equal to 2 del omega n. So as per the characteristic equation, the equation is 2 del omega n. So here the 2 del omega n is equal to 2s. So follow that del omega n equal to 1 because the side term has been cancelled. So del omega n equal to 1. So from that already we know that omega n equal to 2. So 1 by 2, the del value is equal to 0.5. So like that all the characteristic equation of the control systems has been calculated with respect to omega n as well as del. And the poles has been calculated with respect to the particular system of the transfer functions. According to the value of del, a second order system can be set into the four categories. First one is overdamp. Overdamp is the main condition of the overdamp is del greater than 1. So the poles of the corresponding characteristic equations below less than 1. So like that it can be indicated by graph. And next one is underdamp. The underdamp value is the del value must be 0 less than 1. So if it is having minus a minus a to minus c, in between the value as minus b. If it is having an in between value, then the system is said to be an underdamped conditions. And next one is undamped conditions. Del equal to 0. If your poles are locating your imaginary axis as 0, then your system is said to be an undamped conditions. And next one is critically damped. If your del value is equal to 1, then your system is said to be a critically damped. Here it shows that the value of del equal to 1, it may be appeared in the margin of the corresponding graph, so that we can able to calculate the value as 1. It is known as critically damped conditions. So like that, all the values has been assigned and can be mapped with the second order systems based on the transfer characteristics equations. The next one is impulse response of the second order system based on the damping ratio. If it is del equal to 0, then automatically the default equations are followed by the characteristics equations. Del equal to 1, automatically the equation has been changed. If it is 0 del less than 1, then automatically the root has been come with the impulse response. If it is greater than 1, it is a critical damp, then automatically we can forward it as the transfer function by the following characteristic equations. The damping ratio is the one which is used to identify the system function as undamped or underdamped or critically or overdamped systems. If it is overdamped systems, then your frequency may be a high gain value, though those value will be marked in this graph. It can be calculated based on the characteristics equation only. S square plus 2 del omega ns plus omega n square. Assessment how the damping ratio differs with the second order systems. Already we have discussed about the four stages of control systems in damping ratio. First one is undamped, underdamped, critically damped, and overdamped. So if it is overdamped, then your the system function may be greater than one, so that we have to identify the corresponding signals if it is crossed more than one of the corresponding transfer functions. So here all the values has been marked. It shows the different values for different signals, so that we can able to know the corresponding damping ratio for second order systems. Thank you.